Okay, had you made all the arrangements of their lectures for tomorrow?
Yes, we have all the arrangements here. And I want to know how Cornus will give the lectures on board or
On slide. Okay, Carlos will use his iPad and batteries will be using slides.
okay.
Okay, okay, okay. So we have both Aida and Cordian with us now. So this is a research problem discussion session. So who want to go first, Cordian or Aida? Aida, you awake? This is too early for you, so we can go with you first. Aida,
I start first.
yeah, or would
I
you like to
don't.
be second?
I would like to be second also because I should have asked for instructions on like what is expected this hour.
Okay, okay. This is just this is a research discussion session where you can unfold some open problem or something which is still coming in your upcoming lectures, but
Uh-huh.
major conjectures or open problem, what the participant can take.
I see.
Okay, okay. So, anyways, we can go with Cardian first. You can collect your
Okay.
Okay,
collect your
I'm
I
very happy that okay, to be completely honest, I am of course in the same position as Saida. I was hoping that I get instructions.
okay, I can
First,
start. I can
I
start.
can.
I just was not clear, but I can start. Don't worry.
Yeah, I got that. That is what I understood because in your case, this is too early morning in the US, but in Cordian case, he can still manage because this is not that early in Norway, I believe.
I am
For
awake
our
and I
that's
think I understood the task now, and
okay.
I have some quick like answers to give, so I can
Okay.
give time to Cordian. So some of the problems I did mention yesterday are open problems or they lead to open problems, and
Okay.
I try to put problems there that I think they are not like conjectures that like oh, people were stuck for so long but impossible to solve. I try to put their problems that like people can make progress on. Uh, uh so yeah, so those are some like two of those problems that I mentioned are like I would very happy like give those problems to a student of mine to write a dissertation. So like
Mhm.
they are also open-ended problems. What I put there more than conjectures. I like open-ended problems because you can always do some progress and like feel the win. So I would say to go back to those problems, and I'll do the same thing tomorrow. I'll add problems that uh that are unsolved, but the point of the audience is to do some first steps that may be known, but they send to the known problem.
Okay. Okay. I think this makes a good sense, and particularly one can discuss about the asymptotic behavior of algebraic properties under the same
Uh,
invariant structure, right?
yes.
Yeah.
So one thing is, so with Uwe, we started in the last paper. The last paper leaves a lot of things open. So we started the study of this shift invariant, for instance, ideals and algebras, and I gave one of the problems on these topics on shift invariant algebras that are finite up to this shift operator, and the presentation ideals look more like unpredictable. So to give a
Either can you explain by opening the file once again? The file you used
yes,
to share. Yeah, yeah.
yes, I
It
can do that. I can do that. Give me 1 second. Uh, yeah.
yeah. Now you can share the screen.
Okay,
Uh,
give me 1 second. I'll need to
बाकी सारे
open
हैं?
first the file myself. Um, hmm, hmm, hmm. Okay, where are we? Where are we? Yeah, it should be this one. Okay. Okay. When we have had the problem set here, yeah, so the first problems were to get used to this kind of setting. So this one is solved. I just like the problem, and this I think it's simple to nice simple, but to write down the solution. So that was not an open problem. And this was to help with problem 19 and to get used to all that like infinite dimensional ideals and hierarchical models. So problem 19 that I mentioned here, part B, is supposed to be really, if someone is interested in the interface between algebraic statistics and asymptotic algebra, I think this is like a wonderful problem that I have had on back of my head for a long time. But I said, okay, I should share it. So so this is to study how stabilization phenomena contribute to likelihood geometry. And then the problem I was talking right now is problem 20, that is more commutative algebra. So it's the idea is that you here we took the shift invariant subalgebra. Someone can come up with other invariant, but the shift invariant is something we presented and it looked interesting and very easy to define at the beginning. So the problem is take a monomial algebra, let's say a monomial algebra with generated by monomials of degree 2, all monomials of degree 2, and construct this infinite setting where like you left your shift operator, just go to infinity, like send everything to infinity. So we took here x1 square, and then we took all this xi square for any I, and similarly like x1, x2 gives all these xi plus 1s, and this is in three generators up to this shift. So we take algebras that are finitely generated up to this shift, and so by definition they are finite up to shift, construct their corresponding ideals, presentation ideals, as kernels of monomial maps that's mapped to these monomials here. And the question is, when are these ideals finitely generated up to shift? And yeah, one starts with when are the ideals of monomial algebras generated just by degree 2 monomials. So all what is known is like parts that I'm mentioning in this paper, in this problem. But then how to generalize, like how to write a theorem statement equivalent to these examples is not done. So that's an open question, which I think is very doable, and it connects to the next part I'm going to talk tomorrow, finding these finite generating sets and then computing the equivariant or the rationality of the corresponding equivariant Hilbert series for them. So, I don't know if anyone is talking. Okay. So yeah, so I wrote it in a vague way. How can you extend? Because as I said, you can choose to take generators to be, let's say, all like, let's say we take R monomials degree 2 that are quadratic, or one can take two, like one can work on the other direction, takes monomials that increase in like two monomials of degree 3 or of degree 4. It depends on like what kind of direction of research you want to go and what seems also more friendlier. I would personally like to start with quadratics because one can also construct graphs out of them and use the graphs for results. So so my suggestion for generalizing this is to taken monomial algebra invariant under shift, finite monomial algebra invariant under shift, generated by monomial quadratics. You draw graphs associated to them, incident graphs, and such, and try to explore finiteness results associated to these objects.
Okay, okay.
And then and this one also, it's like I think it's a very, very like a rich problem that nobody has studied, but not that they have not studied it because it's not interesting or important, but stage 3 models, they are classical in statistics, but they just entered the world of algebra. So like in fact they are very like this is a very, very promising problem for folks to start working on. And so any result there, like starting exploring, is a new result. Starting figuring, seeing things are new results. Then I say here other problems stated in this what's the name, in this survey. So they work more on like regularity, dimensionality, Betti numbers, finiteness results, and they do state problems there. So if someone is more interested in that kind of direction, I put questions here that are more like unexplored, so they are not tails of some other problem.
Okay, okay. Thank you, Aida. Thank you very much for putting. And can you show that paper? I think for the audience, the survey paper that is by
Yes.
Kubetsky and yeah.
No, that one is here by Junke, Martina, and
Martina Kubetsky.
yes. How can I show it? Can I open it? You mean? Yeah.
Yeah.
Give me
Just
one
to.
sec. Yeah. So 1 second. Yeah, so this is the paper. There is also a published version, but it's in a book. So and they definitely they have problems that are more general, but then they go to I hope this okay definition. Yeah, so another determined constraint. Yeah, so they have problems like this here on the Betti numbers, and some problems are not conjectures. Some problems are written in within lines, not written as problem, but this is supposed to be like for someone in commutative algebra interested in these topics. Is I think it's a very well written in survey. Conjectures. There are many conjectures.
Okay.
Yes.
I think this gives a better idea to the audience. So this is one of the paper,
and
there is a list. Yeah, there is.
And more open problems at the end.
Yeah. Thank you very much.
So I'll do the same thing tomorrow. I will send, in fact, the list of problems by today. And the problems I'm putting are with the purpose of, if someone is interested, they can like follow up that problem to like possibly write a paper or so. And everyone is welcome to write to me if they like make some progress and they want to discuss it with me and check or ask for reference or anything. So very, very welcome to reach out.
Thank you, Aida. Thank you very much. Okay, Gordian, now it's your turn.
Yeah, I'll try to share again and improvise something.
That
That's
is
very
too quick,
dangerous. I have
Cordian.
Huh?
That is too quick.
That
Did
is
you
too quick.
did you solve one of the problem what Aida was mentioning?
No, I want to present, I mean, something that I want to talk a little bit about more in detail on Friday, but it connects a little bit to what. Okay, so can you see my iPad now?
Yeah.
Very good. So I want to come back to, I mean, the lecture that we had yesterday. So yesterday we had, I just have to see how I do this here. So we had defined, we had, I mean, I have, oh, does this work? I'll take the real numbers now for a change. I have the real numbers. I have the polynomial ring, which is defined in polynomials P1 to Pn, where Pn, Pi is the sum of power. I should call this P. Now I have to J to the I. J equals 1 to n. And we had seen yesterday that this is exactly my polynomial ring of invariant polynomials with the action of the natural permutation action of the symmetric group, right? Okay. So this is an actual, I mean, so this is a very nice, interesting ring. And of course, now I can look at polynomials in that ring, right? I can look at polynomials and I can look at the polynomial here inside. So a G in R of P1 to, let's say, Pn for a fixed, which is, I mean, let's do one example. I mean, it could be, I don't know, P1 squared plus 2 P2 P3. It doesn't matter. I mean, this is now just an arbitrary example that I'm bringing up here out of my head. Okay, now I have this polynomial. So this is, if I look at it, if I only look at this polynomial, this is now a polynomial in 3 variables, P1, P2, and P3. Right? It's of degree 2, actually. It's of degree 2 in these variables. Of course, if I remember that these polynomials were actually defined as these polynomials, so in the x variables, the degree of this polynomial is different, right? I mean, this will be a polynomial of degree 3 in the x variables, but now I'm only looking at this polynomial as a polynomial in these 3 variables, and I forget for a moment what these variables actually are. So what I could ask myself is, what is the zero set, of this polynomial? Why doesn't it work? Okay, so I have the zero set P1 of x plus 2 P2 of x times P3 of x equals 0. So the set of x in Rn such that this polynomial is 0. Okay, so this is some real variety. So this is obviously a variety. This is defined by polynomial equations. And now I can look at geometric features of this variety. For example, I could ask myself, how many connected components does this have? How many points, if it's just finitely many points? What are its topological Betti numbers, for example? So I can look at all of kind of geometric quantities that I can relate not to the polynomial, but to this set. Okay. So this set now is a set in Rn. It is defined by these by this expression, which only involves these 3 polynomials, and of course the set that I get has a natural Sn action on it. So if I upstairs find, I mean, if I find any point x in Rn, then also its entire orbit, Sn orbit, will be obtained here. So this will actually make sure, and this we will talk a little bit about, that, for example, the homology groups of this set will have a natural Sn action on them. Okay, now comes the interesting question, and this is something which is only partially understood up to this point. So I mean, if I just hand you such a polynomial, I mean, for example, AIDA could have a polynomial like this, which arises naturally in, I don't know, now I'm just making something up in graph, in some algebraic statistic problem. Some algebraic statistic problem might be naturally expressible in such a polynomial entity. And the solutions, they might count, I don't know what, you know? And it's very important that they're real for some reason. Now, of course, we can tune up this model and say, but I mean, now we have, for example, calculated the number of solutions for n equals 100. And then we would like to understand what is the solution if for this polynomial here, we plug in, instead of n equals 100, n equals 101, n equals 102, and so on. So we will get, and this is what makes it interesting, we will get a sequence of varieties, each of which lives in another space, in an Rn, n plus 1, and so on, has a natural Sn, n plus 1, n plus 2 action on it. And somehow they're all given by the same polynomial identity, which I have here, but the number of variables is naturally growing. Okay, so I mean, now the interesting question is, and this is the question that I still don't know the answer to completely, is, of course, I mean, I can maybe bound the number of solutions that I get with help of whatever Bezout. I can bound the number of homology types and so on with classes for every fixed n. For every fixed n, I will get a natural semi-algebraic or variety in Rn, and I can apply all the results that we have. I can compute these things. But what I would like to understand is not only for each instance, but to understand how these quantities behave with raising n. So what do I mean by this? So one interesting question is, fixing a polynomial like this, is it true that for n big enough and n growing, all kinds of topological invariants of such a semi-algebraic sets, or at least a big class of such, for example, the number of solutions, grows regularly or polynomially in n? Okay, so I say this again, I fix one entity in the power sums or in any other symmetric generators of the symmetric algebra. I look at the sequence of varieties. Each of them lives in a higher dimensional space. And the question is, how does the sequence evolve with n, and then n equals to infinity? What is the limit of this thing? And I mean, of course, I mean, you can cook up examples where you see, I mean, in general, this will be, of course, growing with n. I mean, it will not be a constant most of the time. But the question is, how can we actually get the growth of these topological data when n is growing? So I think this is a very fascinating question, and there have been some results. For example, very recently, Shogata Basu and Shogata Basu has at least one of these papers where they showed that that if you have a very special kind of polynomial, namely if you look at these polynomials here, these polynomials that we take here are just polynomials that are linear combinations of elementary symmetric polynomials. So very simple symmetric polynomials. Then there is an n such that some of these quantities do no longer grow. So I mean, I mean, it's a little bit vague how I'm formulating this. So there is some sort of stabilization happening. Some quantities, not the number of solutions, but the orbits of solutions, so to speak, they get fixed when n is growing bigger and bigger. In general, we have examples where these things just grow. And I mean, it's not that things are not necessarily stabilizing, but still one would hope that one can understand how regular this behavior actually is.
Cordian, can you please show us some computing with this particular example, for instance, how it starts?
I mean, okay, let me give you one example that is, now I'm cheating a little bit because this was, as I said, an example that I just completely made up. So I have to, but let me give you one simple example. Let me give me one simple example that I really like.
Yeah.
So that actually also shows that the reality is important. So let's look at the following example, the following polynomial. x xi squared times xi minus 1 squared. Here's a square. I equals 1 to n, and I want this to be 0. Okay, trick question to the audience. Okay, and I wanted the x, I want the x in r to the n such that this is 0. Okay, so I mean, now we have to, you have to, I mean, this is one polynomial. We could express it in the power sums, for example, and then we would see that with growing n, this is always the same polynomial in these power sums. Okay, but more importantly, looking at this expression here, I bet that it should be possible for at least one person or two persons in the audience to tell me how the solutions actually look like. I claim this is a finite set of points. There's a finite set of points that satisfy these equations. How can you characterize this finite set of points? And you should keep in mind that we want real numbers, and you should keep in mind that there are squares here.
Either 0, 0, 0, 0 or 1, 1, 1.
0, 0, 0 is the solution. 1, 1, 1, 1, 1, 1, 1 is also a solution. Exactly.
Solution.
Is this all
It's just-
solutions?
It's
Yeah.
either 0 or 1.
Exactly. I mean, the
Because
coordinates.
every term here is positive, so every term
Exactly.
must
Exactly.
be 0.
Everything
so
is
this gives
positive.
you either 0
So
or 1.
xi can be either 0 or 1. And if
This-
xi is not 0 or 1, then the point that I have will not be a solution. And
Yeah.
if it's 0 or 1, then it will be a solution. So
There's 2 power n.
Sorry?
Number of solutions.
Exactly. So the number of solutions is just the I mean, so this is exactly the same as 1, 0, whoops, to the n, right? I mean, it's all the points that I get with coordinates either 0 or 1. So this is the cardinality of the 0 set. The cardinality is 2 to the n. Okay, so you see, this is, I mean, this is exponentially growing with n. So it seems a little bit weird. So it's growing, and this is exactly what you expect a little bit when you try to. I mean, you have n equations, and they're of degree 2. I mean, so, but more importantly, this is very regularly growing, right? This is very regular. No, I screwed up.
I have
N
one
squared.
question.
Yes.
We are considering only symmetric polynomial in this case.
In this case, exactly. In this case, I would consider any polynomial. I mean, maybe I should have formulated it a little bit nicer. I should just take a polynomial g in a finite set of variables. I take g. Oops, why doesn't it work? G of z1 to zd for a finite set of variables, which is fixed. And then I look at the substitution set I equals this power sum j to the I. So in that sense, I will always get a symmetric polynomial in n variables for whatever n. I will get with this substitution, I will get a polynomial in n variables of degree whatever, but is symmetric in n variables. And the question is, if I fix this polynomial, if somebody hands me a polynomial g, and I look at all the polynomials that I get in this way, all the varieties that I get by just increasing the number of variables here. So this is a very, very innocent looking problem, right? I just actually change something here. I don't change anything else. So it's really easy to miss this point, but I'm getting a growing number of variables. I get varieties or semi-algebraic sets in a higher number of variables. And the question is, how does this behave with respect to n, the number of solutions? And here we saw it is, I mean, it's not polynomial, but it's still very, very nicely expressible in n. And actually, we will see on Friday that we can actually use representation theory to break this number down in smaller pieces, such that every of the small pieces corresponds to some multiplicities of some representations, and each of these multiplicities then will actually grow polynomial. So the conjecture that we actually have is if you fix the number of variables and the degree of this polynomial here, then you will get a sequence where some equivariant data that you can define for such a variety grows polynomially. So we can actually prove that it grows at most polynomially, but the question would be, can we actually prove that it actually behaves like a polynomial, or let's say a quasi-polynomial, which is almost, I mean, that it behaves very regularly with n and does not really jump around.
Cordian,
This
can
is
you
very-
can you write that statement properly? Then yeah,
I will give
I
you the
understand.
exact, I will give you
Yeah.
the exact statement in my lecture on Friday.
Okay, okay, okay.
But I mean, this was just maybe a very to get people more excited about the lecture on Friday. So this is where we will actually look at this as an example for the use of symmetry, that you can actually break down this thing and understand. And another thing that is related to that is of course, one could ask. I mean, going a little bit to what Aida said about these infinite polynomial rings. I mean, when one has the infinite polynomial ring, there is this natural action of the infinite symmetric group. And we know that a lot of commutative algebra that we have works very much nicer or can be made working, how to say this, classical results of commutative algebra that don't work for the infinite polynomial rings suddenly can be brought into a situation where they work up to symmetry. That's maybe a good statement. At least Aida is nodding, so I did not screw this up completely. Very good. And I mean, a very natural question, which is also up to this point only partially is understood, is how does this actually work on the geometry side? So remember, normally in algebraic geometry, we have a ring, and the nicely behaved ring is always, can be always thought as the coordinate ring of a variety or of a, of course, this infinite polynomial ring is not really nicely behaved. So it's not necessarily the coordinate ring of something that is nice, but one could mod out the symmetry here in this polynomial ring, also going to invariant polynomials in infinitely many variables, whatever this means. It's a little bit hard to see. So this would be power series then. And the question is, one gets a new ring where the group action is neutralized in some sense. And the question is this actually a nice topological space? And this is so far not really understood. So is there a nice topological space where this is the coordinate ring of? Okay, so this was maybe all that I wanted to present, and we will come back to these questions on Friday morning and afternoon.
Thank you. Thank you. Is there anything else other than this question? Yeah, this is a very big question. I think it need more clarification definitely in the upcoming lecture, but this is highly interesting. Thank you very much. Miruna, would you like to open up now? I think you already shared some problem, but would you like to continue?
Just 1 second. Yes. I don't have I haven't prepared. Thank you very much for asking me, but it's the same thing that I said last week.
You already
So
last week. Okay. Okay.
I don't
okay.
have new questions for now.
Okay.
Thank you.
Okay.
This
Thank
guy
you.
Story Glocus
Okay.
and other
Okay.
other variations on this thematic.
Okay. 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 Thank you.
Thank you.
Any question from the IBA side? No. Okay. 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 Probably it's my turn now. Okay. Please screen up. I need to. Okay. Okay, in the previous lecture, just a quick recall of the keywords so that I can describe the open problems and some related results regarding to what we were discussing. So remember, okay, we were discussing about the cut algebras. I hope the audience has noted down everything what was discussed. So cut algebras associated to graphs. So cut algebra give rise to an ideal which we call the cut ideals. And this ideal is of toric type. And one central problem which we were discussing in the course is about finding subgraph and even I can restrict myself to only induce subgraph. For which we have the retraction between the cut algebra of H, in between the cut algebra of H and cut algebra of G. Okay, the bad thing or good thing in any case, in mathematics, a problem is really very nice when you know something about it or even you don't know something about it. This particular problem was basically taken up by Tim Romer and Sarah Madani. So regarding to the cut algebras, you have seen that the ideal grows quite exponentially, and retraction is one of retraction problem in the cut algebra was discussed by Tim Romer and Sarah Madani, and they come up with a very strange kind of construction which give rise to. So I'm just mentioning the result. The theorem says that I don't get the good time to explain the theorem by Romer and Madani. And it says that let G be a simple finite graph let G be a simple finite graph and let H be a, okay, this is something which I could not explain in the last lecture. H be a neighborhood minor of G, then then K of H, the cut algebra of the subgraph H is an algebra retract of Kg. Okay, why this result is important and why I really would like to stress on this particular theorem, and I would like to explain the terminology of the minor, because in the same paper they after giving this particular result doesn't say that this is if and only if. It means that the problem is still open. One can look for other type of subgraph which can give rise to the construction of the algebra retract in the case of cut algebra. The problem is widely open. This is this can be a stepping stone in order to attack this particular problem, to look at the proof, how they attacked it. And particularly, okay, one really low hanging fruit of this particular theorem, they have ripped off already in their paper. There's a series of corollaries which derive through the neighborhood minor. And let me just first of all explain what is this term of neighborhood minor. Let me just explain graphically. So I think rather than putting the definition, the graph, graphically things are more clear. For instance, I'm given with this particular graph. Just try to understand the keywords of firstly the neighborhood minor. Okay, so I told you that first of all the edge. So how I can obtain the subgraph from a given graph. So the first thing is by edge deletion. So for instance, I delete this particular edge. This is a kind of a subgraph of the original graph. And definitely that's why I wrote this is not an induced one. This is the same thing which Sarah also explained in her lecture. This is a subgraph, but not the induced one. Induced one has to include all the edges which exist in between the vertices. But this is a subgraph of the original graph, so one obtained through the edge deletion. And then the other thing is by doing the edge contraction. Edge contraction mean, so I just identify these two vertices together. So for instance, for this particular graph, for the same graph, so I just identify this edge with this one. So I get this one, this new graph. So this is again a graph of the original, a kind of a subgraph, but we don't call it subgraph. And this particular, and any graph which is obtained by applying these two operations on the graph is called the minor of the given graph, a minor of the given graph. You have seen one of the important conjecture. Yeah.
How did the edge between the bottom of the triangle?
These two vertices are being identified together.
Yeah, but how do we get an edge at the bottom of the triangle?
This edge and this, this vertex and this vertex identified together. Identified together. Identified. Okay, this is called the minor of a graph. And don't forget, there's a very important conjecture by Strumfels and Sullivan, which is about the minor. If the graph is K5 minor free, then the quotient ring is Cohen-Macaulay. That is a conjecture which is open, and that is in the keyword. K5 minor mean you are given with a particular graph and you reduce it. If you apply these two operations and you don't obtain K5, so it says that K5 minor free graph. Okay. And you have seen the definition of the cut algebra where vertices and edges, both of them are playing a very important role. You are doing a partition to the set of vertices, and that is giving you the generators, and the generators are coming through the edge set of the graph. Okay. Now the term of the neighborhood minor, which is quite a long. In order to explain the neighborhood minor, for instance, if this is my graph, say this is V1, V2, V3, V4, V5, and V6, V7. So first of all, I need to give you the definition of the neighborhood of a vertex. So there are different terminologies which are needed. So in the same graph, for instance, this is my graph G, and in this particular graph, the neighborhood of vertex 2. So it simply comprises on the vertices which are incident to the given vertex. So it is V1, V3, and V6. Okay. And then there is another notation with the square bracket of V2. That is nothing, just the neighborhood of V2 union. So you include the point as well. So this is one terminology, and even one can take the neighborhood of similarly of a subgraph of the original graph. For instance, I take this is my W prime. This is an induced subgraph on 3 vertices. So neighborhood of this particular subgraph is just the vertex, or in other words, the vertices which are incident to this particular induced subgraph. Okay, so in this case, this is only V6. So I'm just skipping the formal definition. The formal definition can be found in the paper. And now it's time to explain what is the neighborhood minor. That's why I stopped in the last lecture, because the definition of neighborhood minor requires these definitions. Okay, the definition says something like that. The formal definition of neighborhood minor. Let G be the given graph let H be G be a given graph where where the vertex set is the union of the two, and with the this is a kind of a partition with W union W prime is empty set, and both of them are non-empty. And let H is an induced subgraph on W vertices, and with this particular condition that there exists with a vertex V inside W such that, okay, this is highly technical, W intersection with the neighborhood of W prime inside G. So W intersection with this one is contained in neighborhood of the vertex V inside H, not inside W. Okay, I do understand that the definition is quite layered. So this is easy to understand the definition of neighborhood minor through the example. So just consider this particular example. For instance, so for instance, I'm given with this particular graph. Okay, doesn't matter. 4, 5, 6, 7, and 8. Okay, I assume W to be 1, 2, 3. So my induced subgraph GW, or in other words, my H is nothing but this one. This is my H, which is GW. Okay, now I have to look for one vertex, and that one vertex in this particular case is 3. So assume that V is the vertex 3. Now you can verify that. This is a very easy exercise to verify. First of all, take the neighborhood of. Can you tell me by using the definition what is the neighborhood of W prime inside G? So W prime means this whole graph. What will be the neighborhood of this one? It's only 3. Okay, it's only the vertex 3 with which W prime is connected. And now its intersection with W is exactly 3, right? It's only one vertex, so this is also a collection of vertices, NGW prime. The vertices of W prime is, this is 3 and W is 1, 2, 3. So intersection of these two sets is only 3, okay? And now you can see, you can tell me what is NH of V. Can you tell me what is this of the vertex 3? In our case, V is 3. So what is this? It is? So it is 1, 2, 4 आएगा कि नहीं आएगा?
4 नहीं आएगा.
4 नहीं आएगा. Inside H, your 4 will not be a part of it. So only 1 and 2. And definitely this is 1, 2. And don't forget that I'm using the square brackets. So square bracket mean I have to include 3 itself as well. Okay. So clearly this is included in this one. So what does all these calculations shows and what their theorem says that this H, so this H graph, which is a subgraph of the original one, this H is a kind of the cut algebra of this subgraph is algebra retract of the cut algebra of this particular graph. Okay, now I do understand the audience is quite mixed here. There is a series of corollaries, but Sarah, yeah. Sorry.
Go on this definition. The definition is not yet completed.
Oh, definition. Oh, okay. The definition says that if this condition holds, then if the such that this one, then we say that H is a neighborhood minor. H is a neighborhood minor of G. Okay, now the definition is complete, and this is the definition they come up with by looking at, anyways. I think when such a definition and such a condition appeared, it means the authors had gone through a multiple example to see a kind of a pattern which is being used in their proof. And if you understand this particular definition, okay, now there are multiple things. Okay, those who are working in only graph theory, not in algebra. And this theorem can be used as a stepping tool, those who would like to see the classes of the graph or a subgraph, which are, okay, if you think of any graph, and you can think of that particular graph and any subgraph of this particular graph. And if you would like to see some construction which become equivalent to the neighborhood minor, or you can come up, okay, in the same paper, Sarah and Tim, what they have done, they started with 2 graphs, G1 and G2, and they apply some operation to construct a bigger graph. I don't say that they are doing the corona product or they are doing some Cartesian product of the graph. So they invent, in other words, they give a construction of a bigger graph by using G1 and G2. For any G1, for any G2, you give a construction, you built a new graph, and they showed that this bigger graph, which is coming out of this particular construction, this GI is a neighborhood minor. Is a neighborhood minor of G. So this construction, just like the construction of the Cohen-Macaulay graph, which is given in the book of Villarreal, So people are building bigger graph by using the subgraph. So you are given with smaller graph, you construct a bigger graph, and the smaller graph become the neighborhood minor of the smaller graph. So if this combinatorial structure is retained, so you get something really important in algebra. Okay, in algebra, by using this particular theorem, you says that this GI, KGI, the cut algebra of this one is an algebra retract of this one. And a good reference, so there is, let me, the result and I'm stating, I can state it right here. The statement of the theorem, again, this is because this is a construction, so I'm just giving the direction how to attack this particular problem. So if G1 and G2 be two graphs, on vertex set V1 and V2 respectively, and respectively, and let H is an induced graph which is in the intersection of the two induced graph, which is in an intersection vertices of V1 and V2, with the assumption that you are assuming V1 intersection V2, the cardinality is greater or equal to 1. And if H has a vertex, if H has a vertex V with degree of H inside of V inside of H is equal to V1 intersection V2 minus 1, then GI is a neighborhood minor of the bigger graph G. And what is the bigger how they come up with G? Okay, and hence KGI is an algebra retract of KG. Let me just explain. I forgot to, I skipped the detail of G. So G is nothing in this particular case. G is nothing, just the vertex set of G is the union of vertex set of G1 and vertex set of G2. So this they took very straightforward construction. H set of G is again the union of, I don't know in graph theory what people call it. You just take all the vertices and all the edges together with the smaller graph, you got the big graph. And this is a kind of a construction. So again, for the one who are working in graph theory, so you just need to you just need to come up with a new structure, and the new structure coming from the two smaller graph, and so that the smaller graph become the neighborhood minor of the original one. So that then this particular result will apply, and these are small corollaries. So there is a long list of corollaries in their paper where they exhausted this particular theorem. Okay, on one side, this is a very, very low hanging fruit for the one who are working in graph theory to look for the cases where neighborhood minor can occur. But on the other side, this is still an interesting problem to find some other construction which can give rise to the algebra retract. And which can give rise to an algebra retract. as well as the negation. No single negation is known till date, even for the induced subgraph. So up till now, this particular problem is widely open. And at the end of my lecture, I just want to state this particular problem and this particular theorem to to particularly the ones who are interested in only combinatorial side. Still, this is an interesting aspect, just like the construction of Cohen-Macaulay graph. This is again the construction of the graph which give rise to the neighborhood minor, and neighborhood minor is still interesting. You can give a general construction of graph which is coming out of either joining of the two graph, or even for a bigger graph, how you can drop down to having this kind of construction.
So there is a thing that this is a simple union of graphs.
This is I don't know in
Yeah.
graph theory what people call
Yeah,
it.
this is
That this
simple
can be
union,
the
but
simple
it
union.
can be extended to some other operations like the addition of
But
graphs, etc.
you have to be very careful. You have to see that the new graph which is coming, that is the smaller graph, is a neighborhood minor of the original one.
Yeah.
Sorry. Sorry, this is, yeah, they should this put a condition that they should share some vertices. They can't be two disjoint graph. You understand? And this is only in order to use this particular theorem. So this is only one construction I have shown you. In their paper, there is another construction which is called the H sum of the graph. So
Sir, one
a
thing is-
complete sum of the graph.
Sir, please clear one thing, that the GI is a neighborhood minor of G. So the GI
H is a, okay, G1 or GI.
GIs are the two graphs here.
Yeah,
G1 and
the
G2.
two
So
graphs.
you are talking about particularly both, or for
Both.
any of any of? Okay.
So
Both are
GI,
called-
yeah, GI, that means G1 is a neighborhood minor of G, G2 is a neighborhood minor of G.
And
So you got two algebra retract here.
and we get H, and we get H.
H in this case is GI.
Okay, GI is.
Okay.
And the next thing is that, so we should say that the H is a neighborhood minor. So H should be the neighborhood minor.
In this case,
Yeah.
H is the induced subgraph. So basically, in this case, yeah, I mixed something here. There should not be H here. Yeah, there should not be H here. Thank you very much for pointing out. There is no role of H. Yeah, if I would say GI has a vertex, yeah, it's GI. So here everything is in GI. So both GIs are going to give you the algebra retract. Okay, and moreover, there are 3 or 4 more construction which are given. But finding algebra retract is widely open in the theory of cut algebras. So the same cut
Provide a
algebra.
complete reference of this you're mentioning here.
H? Abhi bhi H hai. There is no H now.
At H is equal to G1 intersection. Or
Yeah. Oh.
I think
Everything
that was
is okay.
correct. That was correct.
Yeah, it was correct. Yeah, sorry. I didn't see that. I just wanted to give the reference of the construction they have come up with. Okay. So the purpose is to attack this particular problem. And the reference of this paper, you can, the title of this paper is, those who would like to explore more, is Retract and Algebra. Yeah, algebraic properties. Algebraic properties of cut algebras. And paper is by Tim Romer and Sarah, and this is in 2018. And the journal is European Journal of Combinatorics. The paper contains seriously combinatorical approach almost in all the theorems. Yeah. Okay, that's it from my side. Thank you. Any question from the IBA side or the online audience? Okay, if this is the case,
I-
yeah,
I have a comment
yeah, Ida.
because you are talking about cut algebras of graphs, and I remember to have looked at the papers you are mentioning, and the one connection with what I was saying in my lectures is that for the ideals of hierarchical models that I mentioned, when the simplicial complex is a graph, then the ideal can be thought as coming from like these cut algebras. And this is in the paper of
Thank you.
Sternfels and Sullivan. So you just do a suspension of the graph and you get the cut ideal of that suspension. It's the same as the ideal of the hierarchical model. And also, with some collaborators, in one paper, we generalized these cut algebras and ideals to simplicial complexes. So like going from graphs to simplicial complexes. So if you want problems that are like, how to extend the theory, then yeah, we started there. And the paper is called Generalized Cut Polytopes. In fact, because we all worry about the polytopes, but there is a
In the same paper, they also discuss cut polytopes because this is it has very natural correction with that. So
Yeah.
I
But you can
this is quite
study
understandable.
the generalized cut ideal or cut algebra. Like the definition is there. We just cared in that point. We cared about the polytop. So nothing else. The generalized version is not studied at all combinatorially nor algebraically, and so.
Okay, it's time to say goodbye to everyone and especially to our speaker Carlos and Beatriz. They are departing for Karachi today. Thank you. Yeah, see you online. See you tomorrow on online. Okay, Aida. Okay, Cordian. Okay, Meruna. Thank you very much. Our online audience. So we are here saying goodbye to our guests who are now traveling here. So they have many friends. So everyone is going out to say them goodbye. Thank you very much, Cordian. Thank you, Aida, for coming. So see you tomorrow. See you tomorrow, everyone.